Hello everyone, welcome to the class ECE317 Digital Signal Processing. Today we will keep working on the structure of systems. The ECE317. This is the 11th week, Friday's class. Okay. So about the structures of systems. Okay, I do some examples today. All right, consider example. Yeah, not a complex one, but I want to explain something related. Consider system h of z equal to 1 plus 2, 3, okay. 3 z to negative 1 and 1 minus 3 z to negative 1. Now consider system looks like this. Then this one, what kind of structure can we have? We have several, right? We have several. We know we have numerator, we have denominator. You can put the numerator part in the front or in the back. Right, then you have two different choices, and then each part you want the delay in the left side or right side. Right, actually totally we have 4 different types. Then the problem is which one is better? Okay, here of course you have problem. So what do you mean a better structure? Right, you have different structure. What do you mean a better? Okay, let me just write 2 different one as an example. We can have like we use a direct form 1, and then the other is a direct form 2. I give 2. Okay, direct form 1. Direct form 1, we have the I write this. Okay, I do not merge them. Then they will be separate. This one is forward and this one is backward. Okay. And I have delay here and delay here. This is direct 1 form, and the numbers 1 and 3, so 1 and 3, and here will be negative 3, so this is also 3. Alright, so we have the structure direct form 1 is this, and the direct form 2, I still use the 1 didn't merge together. Alright, yeah, you can also merge like this one, you can merge together. I just use the one I didn't merge. Then direct form 2. Direct form 2, then delay will be in the front. No, not delay. I mean the feedback will be in the front, and then the forward part. The numerator is forward part. Right? This is for numerator. Coefficients 1 and 3, and this is the feedback part. According to the denominator, it's a negative of negative 3. It's a 3. And the delay, direct 2, then the delay will be in the middle. It's direct 2, yeah, they in the middle. This is a delay, up to delays. Alright. Then for the which kind of structure is better? We have several different considerations. The first one is about the cost of the system. First one, consider the cost. I say the cost of the system, of the field. For the direct form 1, for this one, you can check in the input side. You have a delay here, right? a multiplication by 3. Here's a summation, right? And then here's another summation, and here's another delay, and here's a multiplication by 3. So we have 2 of delay, 2 of summation, and 2 of multiplication. Let's see, multiplication, right? I have these 3, 2 multiplication, 2 delays, and 2 summation. I use a diamond for the summation, right? This is for this one. And the direct 2 type, how many summation, how many delay? I still have 2 of delay and 2 of summation, right? Here's a summation, here's a summation. I have 2 summation. This is summation, this is summation, right? Do we have any other summations here? No. Here? No. Actually, only 2 summations, right? 2 summations, and 2 of multiplications. And then we can merge this part. After merge, the middle path, right? I can merge these 2 together, or merge these 2 together. Then what happened now? For the direct type 1, I still have 2 delays, 2 multiplications. For summation, I change it to be 1 summation, right? Or still 2 summation, because these 2 put together. These 2 put it together. Then here I have a summation. Is this one add this one, right? I have 1 summation. Then going up, here's another summation. So I still have 2 summations. So this is a 2 summation, 2 delays, 2 of summation. I write in this way, and 2 of multiplication, right? And this one, after we merge 2 summation, these 2 are summations, right? Still 2 summations, and the delays merge together. So I have 1 delay, 2 multiplication, 2 of summation. How many summation? This is summation, right? This is a separate. This is summation. Oh, 3 summation. These 2, right? You merge these 2 together. When you merge these 2 together, do you need a summation? Oh no, this is not summation. It's a signal separated as 2 paths. One is going down, one is forward. And going down one, after delay here, go to here, then separate to left and right. So this is not a summation. It's a separate as 2 directions. Okay, so no more summations. But this one is still summation. This one is still summation. So I still have 2 summations. And the multiplication, 3 and 3, they are still be there. So I have 2 of multiplications. Alright. Then here you can compare. You see, you save 1 delay here. So this one is better. This is better in the sense we can save the cost of the calculation. Right? We have name. We call this is a complexity of the system, of this field. Complexity. And the complexity is actually they have 2 complexity. One is the time complexity. One is space complexity. We have 2 different kind of complexity, time and space. Okay, here I just check the time complexity. Alright, let me see. We can consider both. Then for here we have delay, we have summation and multiplication. So what will be the cost of these kind of things? So for the complexity, we have the one is for time, one is for space, right? And we have several operations. We have a delay, we have a summation, we have a multiplication, and here this operation on we say the numbers, they are n-bit digital number. Right, n-bit digital number, like some bit like 16-bit, 32-bit, or 64-bit, depending on the computer and the operation systems. Right, so you have different lengths for a number. Suppose n-bit. Then the complexity about for the delay, that is I write in this way. This is like a constant. Yeah, it is just constant. And then summation, that will be something related with n. And for the space complexity, I think it's less. Maybe it's still this one, similar with this. Right. And for multiplication, the time will be related with n squared, and the space will be related with n. Actually, here they are not exactly this one, depending the operation, depending the algorithm of the operation. For different algorithm, the multiplication maybe they will run faster. Some algorithm run faster, but usually the faster algorithm they need more space. And if the algorithm can save some space, then it will run a little bit longer. But roughly speaking, we can think these three operations, the complexity, the cost of time and space can look like this. Alright, so we can say if we can have less multiplication, then the structure will be better. Right. Of course, any kind of operation, if you can reduce the amount of those operations, that will be save something, so that will be better. But the multiplication is cost more times. So if you can try to first of all, you can try to reduce the amount of multiplications. Then we go back to this example. For these two operations, for these two structures, we already have the whole amount of how many multiplication, how many summation, how many delays. Right? We listed the result here. Then can we find the structure? We can save more, more multiplication. Actually, this is a special field. The h of z looks like this, right? These two numbers are same. Here's a plus 3, here's a minus 3. And then you look at the structure. I have two paths. This one is 3, this is also 3, right? This one is 3, this one is also 3. So can we save? Because both are 3, can we do these in one place? Right? If we can rewrite the structure, we only have one multiplication. Maybe that will be better. Then we can try. Can we do that? Okay, you look at it here. This is going down, right? These two, I say I can merge these middle two, so these two delay can merge together. After this, you will see, after you merge these two together, then one go left is times 3. Go right is also times 3. So actually, it's very simple. I can just merge these two, or also merge these two together. So now we can consider like this. Now we use structure like this. here's a delay. I merge these two delay together, and then times 3, right? Times 3 here, and then going up, separate. Okay, so you see this one and this one, these two structures, actually same thing, right? Same thing. Yeah, this signal going down with a delay, then times 3 to left, times 3 to the right, right? Is here. Okay, then we can check this one. How many operations do we have? How many delays? We have 1 delays. One of the delay, and one of the, or 2 of the summation. Summation is also still 2. This is summation. This summation, right? This summation because I have 2 signal go into it, 2 or more signal go into it. Then this is summation. Here's also 2 signal go into it. This is summation. This is no. This is not summation. Just 1 into, then separate to left and right. Right. So this is summation, this is summation. I have 2 summations. And then multiplication just here, times 3. You see? Then we save more, right? This one save more. This one save more. If you just look at here, you think, okay, it's nothing, just to save 1 multiplication. It's not a lot. Actually, it saves a lot because like if you run these, you signal go into that side and that side coming give output. If you keep this running like 1,000 or even million or billion data go over it, then every number, for every input you save something. Right? So that saves a lot. That saves a lot. Okay. So this is one thing we consider the. Okay, this one, this structure. Save more on time and space complexity. Right, so we have this. Okay, this is one consideration. The time and space cost when you run this system. And another thing we need to consider is when you run it, actually this is a digital system, right? It's a digital. When you run it, you use a digital. So every number when you do calculate, it is not the exact value. It is just the digital value. It is a value like depending on the length of the word, of the number. Like you have m bit, or you have like a 32 bit, you have 64 bit. Then that gives you a limit. When the number is you need more accurate, you can't. You only have those can represent by m bit. For example, you can think of the pi and the 3.14. Of course, this is not use 2 as a not a binary number. This is we use a 10 as to represent number, right? Like this one, this is a pi, this is real number, and this one you can think this is with 2 digit, 10 as a digit, 10 as a digit, right? So you have 2. After dot you have 2. Then the accurate is just like this. After this 4, 3.14, as a pi you have more numbers, but here you will drop them. When you do the digital calculation, you always do like this. When you have number, after the number, several digit, you only have limited number can be used, right? So we have another thing. We have we call this a round up, a round off or run off arrow or noise. You will consider this one. You just look at the structure. For example, suppose you have some, you see here you have a loop here, right? You have loop here. Then if you have like here you have a round off, then you cause some error, right? Then when you're going down, turn around, this round off will keep here, and maybe even become a little bit larger. Then turn around. After several times, maybe the arrow were accumulated to be a very large number. So when you give the structure, you will consider where do you have the risk some runoff around the up arrows or turn to be larger and larger, then like go to infinity. Yeah, so you need to consider that. The different structure, these arrows were changed in different way, so you will also consider that. Here I don't do that. I just give you the consideration here. You read the textbook, there are 1 or 2 sections related with this kind of things. Yeah, and actually 2 sides. One side is for the date, that's for the input signal, output signal, right, for these signals. And another thing is for this parameter. Here, like the parameter 3. If this parameter, for example, if this is pi, then the parameter itself, you have to do some runoff for the parameter. So you have the parameter happen in 2 places. One is happen for the signals. Every signal, like this is a x of n. Here you have a w of n. Here you use a z. You have a z of n. Here you have a beta of n, for example. Then all these signals, you will have kind of runoff. And another kind of runoff is for these coefficients. You also have some runoff. Then all of these will cause some arrows. So when you give a structure, you will consider the arrows were not accumulated to to make everything wrong. Cannot be too much. If those run up or run off arrows can be as a limit, will tend to be a small value or even tend to be 0 after they run in the system, that will be good. But if the arrow will be emphasized to be larger and larger, then that's not good. Okay, that's another consideration. Alright, here we focus on the space and the time complexity here. Alright. Okay, we check another example we can consider. I still consider the complexity. H of z, now I still use 3. Okay, 3 plus z to negative 1 over 1 minus 3z to negative 1. Now this is another system. Here you see I choose 2 parameters. I have 2 threes. Actually, when you give structure, we will consider with a structure with I put 3 together, that will be fine, right? Okay, for this one we can have the structure. Basically we use direct form, right? Direct form. I use direct form 1. Then I put the forward part firstly. Then feedback, the denominator followed. Right. Okay, then I have delay here. And the coefficients, numerator I have 3 and 1, so 3 is here, 1 is here. The 1 is nothing, I just do not need to put anything here. And then the feedback is depending on the denominator. I need 3 here. Yeah, here's a minus 3, then here you put 3. Okay, then you look at it. This structure, I have 2 multiplications. Can I put these 2 together? Now this is a direct type 2, direct type 1. Okay, direct type 1. Can I put these 2 together? Yeah, this is a problem. If I can put these 2 together, then I can save something, right? Okay, you look at here, this part. Actually, this is a 2 paths, right? One is going use the upper band, you have 3, and this is the lower band, you have negative z to negative 1. You have delay. So this part I can write it in this way. 1 is 3, 1 is a delay. right? 1 is a delay. And this one, here's nothing, just 1. This one I have two part. One part is 3, one part is a delay, right? Look like this. Okay, you can see this is upper band is 3, right? I can flip these 2, you get same thing. So this is a delay, this is 3. These are same, right? Delay here, this is 3. Okay, you see, now I can put these 2 together. Can I? Yeah, I can put it together. You can think like this. This is a delay here, and this is a 3. This is delay, this is 3. Alright, these 2 I can put them together. Just so I add these 2 signals together, then times 3. So I can work like this. Here is still the delay, and here is a summation. This is a Z to the delay. Right. I do summation. After the summation, I put a 3. Okay, I have a structure looks like this. Alright, I can compare these 2. This one, I have how many delays? I have 2 delays. 2 delays. I use square. 2 delays. And how many summations? This is summation, right? I have 2 signals go into it. This is also summation. So summation, I have 2 summations. 2 summations. I put like this way. And the multiplication, this 3 and this 3. So I have 2 of the multiplications. So I have these 2, 2, 2, right? If I merge these 2 together, after merge the middle lines, I have then these two merge together. So here's the summation. Then here's also summation. So I still have 2 summations. 2 summations, and delay Z is here. So still 2 delays and 2 multiplications. Yeah, this one for direct type 1, you merge the middle 2 paths together, nothing change. Right, nothing change. And this one, how many delays? Still 2 delays, right? 2 delays. This is 1, this one. And how many summation? You can see this is a separate. Here is a summation, right? And then coming up here is still 2 summation. Okay, 2 summations. And then multiply by 3, only 1. So 1 multiplications. Now we have these. So you see, by this way we can also say 1 multiplication. Here's a 2 multiplication. Now I have only 1 multiplication. Alright, give 1 more. Yeah, for high order is complex. I give this one. I give a system look like this. It's a FIR field. I use this one, H of n. The impulse response, it is 2, 3, 4, 4, 3, 2, and here's n equal to 0. Okay, H of n is this one. Then that means the Z transform of these, the transfer function, will be Z transform of impulse response, right? That will be 2 times Z to 0, and 3 times Z to -1, and 4 times Z to -2, plus 4 times Z to -3, plus 3 times z to negative 4 and 2 times z to negative 5. Alright, this is the transfer function. Then, okay, this is a FIR field, right? FIR field. Then we have the structure. We know the structure can be written in this way. Just forward. I have 1, 2, 3, 4, 5. I need 5 delays. 5 forward after delays. So here should be delay. You can put it either way, either side. Okay, just put here delay. I need 1, 2, 3, 4, 5 delays. 1, 2, 3. Yeah, until 5 delays. 1, 2, 3. I need 2 more. So delay. Put a small circle here. Alright, and this side is coming up. And the coefficient 2, 3, 4, 4, 3, 2. Alright, so we have structure look like this. You can also put the delay in the right side, similar thing. Now you look at this structure. Obviously, you see, you have 2 times with 4. Right? You have 2 paths. These 2 paths, you need a times 4 on the signal. So you have a signal coming from here, then going down with delay, then go through this path, you need times 4. And go to next path, you also need times 4. Similar, you have 2 multiplications with 3 and another 2 multiplications with 2. So you can think, can we merge these multiplication by same number together? Right. That will save you multiplication. Now you have 1, 2, 3, 4, 5, 6 multiplications, and we can try to reduce them. Okay, we can work like this. This one and this one, you see, times 4 times 4, and after you times 4, you will do summation on, or you add all of these together, you can have the output, right? Then you can think, okay, these two I add them together before I times 4. Then I only need times 1 of the 4, right? So we can consider like this. Okay, this is 2, this is 3, and this one I need times 4, and this one is also I need times 4, right? So I add these 2 together and then times 4, right? I can work like this. And then for 3, actually we can do the same thing for 3. This one is also 3, right? This one is 3. So I go to, like, I put the dot here, and this one go to here, and 3 just for this part. This 3 just for this part. I add these 2 together, then times 3. And similar, I have 2, right? So after here, and this is the delays. Delay, and the delay, I have 5 delays. Okay. This one, the signal here, I want to go to here. So, let me go this way. And add them together, then times 2. Okay, by this way you see, 1 multiplication, 2 multiplication, 3 multiplication. I only have 3 multiplication in this structure, and of course this one I need added to here. So add it to here, or maybe add it to here, doesn't matter. Yeah, make sense? Can I put it in a more, looks better? This looks a little bit not so tight. Okay, it works, right? It works. This one plus this one times 3, this one plus this one times 4, and this one plus this one times 2. After you times 2, 3, 4, you add them again, then you have the output. Yeah, this is right one. This is right one. and we can check how many delays, how many summations, and how many multiplications. So delays 1, 2, 3, 4, 5. I have 5 delays. 5 delays. And summation. So okay, here's a summation, right? Here's a summation. These two add together. And this one to here, this is also a summation. And this one go to here, this is also a summation. So here I have 1, 2, 3, 3 summations. And after these 3, I go ahead to here a summation, to here a summation. So I have 2 more summation. Totally 3 plus 2, so 5 summations. And then multiplication. Multiplication only times 2, times 3, and times 4. So I have 3 multiplications. Alright, so this is for this structure. And this structure, we look at this one. This structure, I have 1, 2, 3, 4, 5. I have 5 delays. And how many summations? Yeah, this side is just separate. The summation, we have summation here. 1, 2, 3, 4, 5. 5 summations. 5 summations. And then how many multiplications? Okay, 2, 3, 4, 4, 3, 2. All of them, they are multiplication, right? So totally, I have 6 multiplications. Then obviously, you see, we save 3 multiplications. I can say this saves a lot. This saves a lot. Alright. And of course, this graph looks not so good. Can we rewrite it, make it better? Looks better. Oh. This one looks okay. We can like this. Here's a delay. Here's a delay. After 2 delays, I have a delay. Then these 2 will go together and times 4, right? Times 4. And then after these 2 were put together. Yeah, I can work like this. Delay, delay, right? Totally I have 5 delays. I have 2 here, and then go to here, then coming up, coming up. This is also delays, delays, delays. And these 2 times together, add them together. This were times 4. And these 2, I add them together. And start from here, I need a times 3. And these 2, I add them together. After these, I need a times 2. Right. So then I go to, like suppose y this side, I will go to here. And I go to here. And I go to here. Then these I do summation. I do summation. Then I have y. This is a input. This is output. Yn. Right, look like this. Or I mixture. If I use signal flow graph, I just need a small circle. I don't need this cross here. Just a small circle will be fine. Small circle will be fine. If this looks better, a little bit better. Okay, anyway, yeah, the structure looks like this. Then after the summation, here I need a times 4. Here I need a times 3. Here I need times 2. Okay, then I have the structure looks like this. Yeah. So in a lot of systems, when you consider the structure, you can consider the multiplication. If they times by some same numbers, then you can try to merge that 2 paths together. Of course, sometimes maybe you can't, but sometimes you can do it. You can do it. All right. Yeah. Okay. Okay, I will say that's all for today. Actually, I just want to introduce the time complexity, the space complexity, and also I talk a little bit about the runoff and run-up arrows. They are related with the structures, and this part will not be in the homework, will not be in the exam. I just introduce some knowledge to here. You can say this class just kind of summary. And in the homework problems, in the textbook, in the textbook, after chapter 6, you have some homework problems, right? Some exercise problems in the textbook. You can find there are some homework problems related with that. Now, not really homework. I don't give you that as homework. You can say it's a practice problem. Practice problems. I only remember one. Photo 5. Yeah, if you're interested, you can try that problem. You need your structure is given, and you need to check the how many summation, how many multiplication, how many delays in that structure, and then you can try to do something to reduce some operations, reduce some summation or reduce some multiplication or something like that. All right. Okay, that's all for today, and today is Friday, so wish you all have a good weekend. All right, bye bye.